Hi, my name is Glenn Weinreb, and today we're going to talk about how much it costs to fix the climate problem. And this is part 11 of our Climate Solution video series. The public is inundated with information about climate. Some reports focus on the problem, whereas other reports focus on initiatives that reduce carbon dioxide emissions. Unfortunately, many initiatives are not effective or not cost-effective. This is because people sell climate to make money, and the impact of their efforts are rarely quantified. This begs the question, if we instead resolve climate change for real at the lowest cost to society, what would we do physically and how much would it cost? This question is of profound importance, yet is rarely discussed. We will explore this question in this video. But before we do, let's review the climate problem. The average global temperature in September of 2023 was a half a degree warmer than the previous warmest September. The surface area of Antarctica sea ice in July of 2023 was 1.5 million square kilometers less than the previous record. The measurement that keeps climate scientists up at night is shown here. This is a plot of global warming versus time as seen by satellites. They see one blanket around the planet due to 150 years of carbon dioxide and methane emissions, and they saw a second blanket of similar size appear over the last 10 years. This second blanket is not explained by carbon dioxide, methane, or tipping points. I know this sounds crazy, yet this is what is observed by NASA satellites, and this was the focus of the most important climate paper published in 2023. What is happening? This is a big mystery. Climate models did not predict 2023 observations, which implies they have one or more bugs. One possible explanation is air pollution reduction over the last 10 years may have inadvertently increased global warming. This is because sunlight reflects off of air pollution and back into outer space and therefore cools the planet. And when we reduced air pollution over the last decade, we might have also reduced this cooling and subsequently increased warming. Satellites measure characteristics of our atmosphere. However, there is one parameter that is difficult to measure. It is the amount of sunlight that reflects off of air pollution. Due to this monitoring blind spot, climate scientists have not been able to fully understand the atmosphere. Our conundrum is illustrated here. The length of the red bar represents the amount of global warming that has occurred over the last few hundred years. And the length of the blue bar represents the amount of cooling due to sunlight reflecting off air pollution. These two combined to yield observed warming. The upper graphic shows a moderate amount of global warming offset by a small amount of cooling from air pollution. We refer to this as Planet X. And the bottom graphic shows a larger amount of warming offset by a larger amount of cooling. We refer to this as Planet Y. Unfortunately, due to our monitoring blind spot, we have not been able to measure the length of the blue bar. Subsequently, we don't know if we are on Planet X or Planet Y. In both cases, the observed warming is the same. However, there is a significant difference between these two planets. Planet Y climate models expect many ecosystems to collapse over the next 30 years, whereas Planet X climate models suggest we have more time. In other words, Planet Y is a bad planet. This raises a fundamental question. Do we live on Planet X or Planet Y? The answer has profound consequences. The IPCC reports that appear on the desks of national leaders assume we are on Planet X, and policies therefore reflect this understanding of the world. However, there is evidence we are on Planet Y. More specifically, climate models based on Planet Y are better at predicting observations. We need to prioritize the development of instrumentation that measures how much sunlight is reflected off air pollution so we definitively know what planet we are on. For more details on our measurement conundrum, consider Sabine Hostenfelder's excellent video. I understand the title of this video is How Much Does It Cost to Fix the Climate Problem? We will get to that in a moment with cost estimates that assume we are on planet Y. Scientists 30 years ago stated the world needs to avoid a 1.5 degree global temperature increase or bad things will happen. They did not elaborate on what they meant by bad things, perhaps for fear of appearing too dramatic or crazy. At approximately 1.5 degrees, additional sources of warming begin to activate and add to the warming already being done by carbon dioxide. In other words, global warming accelerates due to additional warming sources. And this occurs faster on planet Y than on planet X. The additional warming sources are commonly referred to as tipping points. The first to tip will probably be North Pole sea ice. This is expected to melt over the next 15 to 20 years, and this will result in more global warming since sunlight is absorbed by seawater instead of being reflected by sea ice. The surface area of this sea ice is considerable. More specifically, it is 5 million square kilometers, and losing its reflectivity would cause the average global temperature to increase an additional 0.6 degrees Celsius. Keep in mind, North Pole sea ice is just one of many tipping points. Unfortunately, warmer Arctic seawater will cause the ice on Greenland to melt more quickly, which will cause the sea to rise. This is expected to occur geometrically, not linearly, which means it is not likely to have a big impact for several decades. However, between 2050 and 2150, we can expect multiple meters of sea level rise. What else? Well, storm intensity is expected to increase, and a number of large forests are expected to dry out and become savannas. It is difficult to wrap one's head around the concept of a different planet. For example, during the Ice Age, 24,000 years ago, we had a slab of ice 2.5 kilometers thick on top of what is now New York. The difference between that world and today's world boggles the mind, and that was not long ago. The average global temperature of 2023 relative to 120 years ago is 1.42 degrees Celsius. In other words, 1.5 degrees is in the process of arriving, and we are seeing glimpses of tipping points. I know all of this sounds terrible, yet it can be resolved with minimal disruption, as we will discuss in this video. We primarily have two climate problems. One is global warming from carbon dioxide, and the other is global warming from tipping points. We can resolve the carbon dioxide problem by replacing fossil fuel with green energy. And we can resolve the tipping problem by reflecting a tiny percentage of sunlight back into outer space. This can be done by placing material into the atmosphere. Unfortunately, we probably cannot resolve the tipping problem by reducing carbon dioxide, since we seem to be tipping too fast. Scientists have done back-of-the-envelope calculations on the different ways to block climate tipping points, and one approach stands out. It is to inject material into the atmosphere at a 20-kilometer altitude above where airplanes typically fly. Due to the layering of cold and warm air at this altitude, injected material would stay aloft for 1 to 2 years instead of quickly falling to Earth due to gravity. Other planet cooling approaches are orders of magnitude more expensive. Increasing reflectivity is a new field, and there are many things we do not know. We do not know what to inject, where, when, and how, and we do not have an accurate assessment of costs and adverse side effects. To resolve unknowns, we would need to spend billions of dollars on R&D. This includes developing better instrumentation for measuring atmospheric reflectivity, developing equipment that injects small amounts of material for field experiments, and developing equipment that injects large amounts of material for full-scale operations. At this time, there's no demand by the public to touch the atmosphere. However, as evidence of climate harm increases, this is likely to change. Our society is already putting large amounts of material into the atmosphere when we burn fossil fuel. This would be similar. However, the amount injected would be less, and it would be injected to a location far from people. On the bright side, no pun intended, only a tiny percentage of sunlight needs to be reflected. The public would barely notice. To justify the expense, our society would need to compare the cost of cooling the planet with the cost of not cooling the planet. One study suggests large-scale planet cooling would cost $18 billion a year. For comparison, the total value of New York City property is $1,300 billion. And this is just one coastal city that would be lost to sea level rise. If the United States paid half and R&D costs $3 billion a year, we can calculate the cost per American per year. The math works out to $5 per year for R&D and $30 per year for actual planet cooling. To block the first climate tipping point, we might need to begin atmospheric intervention 3 to 10 years from now. And we would need to do R&D at the billion-dollar level for several years before that deployment. As mentioned previously, we primarily have two climate problems. One is global warming from tipping points, and the other is global warming from carbon dioxide. We can solve the tipping problem by slightly increasing the reflectivity of the atmosphere, and we can solve the carbon dioxide problem by reducing carbon dioxide emissions. However, our society is already doing that, and many programs are not effective or not cost-effective. Globally, carbon dioxide emissions are increasing, not decreasing. We are failing because we ignore basic principles of economics, government, science, and engineering. If we instead adhered to principles, fixing climate would be easier. We will now look at what would happen if we tackle the climate problem at lowest cost using basic principles. From an economics perspective, this involves initiatives that reduce carbon dioxide emissions. Each initiative has a cost and an amount of carbon dioxide that is reduced. One can divide these two numbers to calculate the dollars needed to reduce emissions by 1 ton of carbon dioxide. For example, when buying an electric vehicle instead of a gas vehicle, it typically costs over $200 to reduce carbon dioxide emissions by 1 ton. And when a homeowner places solar panels on their home, it typically costs over $100 to reduce carbon dioxide emissions by 1 ton. Alternatively, when building a solar farm or wind farm, it typically costs $20 per ton. These numbers are important since they have an enormous impact on how government approaches the climate problem, as we will discuss in a moment. If a nation reduces carbon dioxide emissions 1/30th each year over 30 years, it will get to zero 30 years from now. One can divide total emissions by 30 years to calculate the number of tons of carbon dioxide that need to be reduced each year. For example, U.S. emissions are approximately 5 billion tons a year, and this, divided by 30 years, is approximately 170 million tons. In other words, the U.S. can reduce emissions 170 million tons a year for 30 years to reach zero 30 years from now. We can multiply 170 million tons times the $20 per ton decarbonization cost to calculate the total cost per year. And we can divide this by population to calculate the cost per American per year. The math works out to $10 per American for year 1, $20 for year 2, $30 for year 3, etc. These costs show up as an increase in the cost of goods and services, since green things typically cost more than non-green things. These low numbers tell us we would not have a cost problem if we tackled climate with cost-effective initiatives. According to survey, 67% of Americans are concerned about climate and want to reduce carbon dioxide emissions. This tells us we do not have a support problem. To better understand this, we need to examine statements made by representatives. Many are asking, why spend $200 to reduce carbon dioxide by 1 ton when we can do it for 20? In other words, support increases when cost per ton decreases. In effect, this means the majority requires that decarbonization occur roughly in lowest cost order. For example, tackle $20 per ton programs followed by $25 per ton. Also, this implies it is not necessary to tackle high cost per ton areas during the early years. All that matters is that emissions decrease roughly 1/30th each year. Decision-making sometimes involves a reasonable and mature process that has majority support. For example, if a nation wanted to develop a climate plan, they might commission a study. More specifically, they might ask government economists to identify how to transition to a green economy over 30 years at a constant rate at the lowest cost to society in lowest cost order with additional costs passed on to consumers. In other words, do the dotted green line at the lowest cost to society. Government economists would then produce a decarbonization report with a list of suggested initiatives. And for each, they would estimate cost and amount of carbon dioxide reduced. And they would divide these two numbers to calculate cost per ton. Liberals tend to support all climate remedies, whereas conservatives concerned about climate tend to only support low cost per ton remedies. A study might help them identify a grand climate bargain that meets the satisfaction of both sides. In other words, conservatives might agree to 1/30th carbon dioxide reduction each year in return for less high cost per ton activity. If an agreement was reached, a national climate plan would emerge. Companies must keep their costs down to be competitive. Therefore, they cannot afford to pay additional costs for greener products to be so-called good citizens. However, if everyone in their industry is required by law to go green and pass additional costs on to consumers, they will proceed as required using the lowest cost method. In other words, government requirements can use capitalism to achieve lowest cost decarbonization at large scales. Here's an example. A new law could require power companies to decarbonize the electrical power grid by a specific date and pass additional cost onto consumers. Builders of solar farms and wind farms would then compete with each other and drive down costs. Ultimately, $20 per ton decarbonization would occur at large scales. Decarbonizing in lowest cost order means that the early years would be relatively easy while the later years would be more difficult. To make life easier for tomorrow, we can do more R&D today. There are dozens of large R&D initiatives that are currently not being done that have the potential for significant impact. Here's an example. Scientists are currently studying how to generate energy with a hot plasma inside a donut-shaped structure. This is referred to as tokamak fusion, and it is not expected to be commercially available for another 20 years. However, a billion-dollar-sized R&D initiative could potentially get this done sooner. Here's another example of a large R&D initiative that is currently not being done. In theory, we could develop next-generation buildings where each device in the building has a processor that can reliably communicate with all other devices in the building. Devices include appliances, heating and air conditioning equipment, lights, motorized dampers in vents, temperature sensors, occupancy sensors, motorized thermal covers for windows, etc. This would enable buildings to reduce energy consumption via multiple techniques. For details on these ideas and others, please refer to this free climate book. Globally, new green infrastructure is likely to cost $100 trillion. Therefore, it is reasonable to spend additional billions of dollars on R&D to save trillions on infrastructure. If more R&D costs $20 billion and the United States paid half, the math works out to $30 per American per year. And for 10 pennies per American, a proposal writing fund could pay researchers to write proposals to work on large R&D initiatives. Okay, let's get back to our original question. How much does it cost to fix the climate problem? The answer is summarized in this table. All numbers are in units of dollars cost per American per year. Europeans would see similar numbers. These costs would show up as an increase in the cost of goods and services in addition to money spent by government. Costs are divided into three categories: planet cooling, decarbonization green premium, and additional R&D. We assume decarbonization occurs over 30 years at a constant rate, and we assume decarbonization green premium costs start out at $20 per ton of carbon dioxide reduced and increase over 30 years to $80 per ton. The left part of the table looks at years 1, 2, and 3, while the right part of the table looks at years 10, 20, and 30. One might think of these as the early years and the later years. The early years are relatively easy since green premium costs are proportional to the amount of carbon dioxide reduced, and initially this is small. Evidence of climate harm also increases with time. Therefore, the public's tolerance of costs is also likely to increase. In other words, to survive climate change, we need costs to stay below tolerance of costs as we go through time. For example, we need the public to support approximately $50 per American per year during the early years when people are moderately nervous about climate, and accept hundreds of dollars per American per year during the later years when people are more nervous. For the most part, no one wants to touch the atmosphere. However, we are already doing this when we burn fossil fuel. Also, it is possible we need to touch the atmosphere to save the planet from an insane sequence of events. This begs the question, how might we do this responsibly? Sulfur is an element in the periodic table, and large amounts of sulfur are contained within coal and oil. For this reason, sulfur is emitted into the atmosphere when these are burned. Sulfur in air is bad for two reasons. One, it is not healthy to breathe, and two, it increases the acidity of the ocean. For this reason, governments often require it to be filtered out before or after combustion. Even with some filtration, approximately 100 million tons of sulfur are emitted into the atmosphere each year. We will now look at what typically happens to sulfur after it enters the atmosphere. It starts out as SO2 gas, and it typically combines with water and oxygen to form H2SO4 gas. It then nucleates, which means it converts to a tiny physical particle. Water sticks to this particle and eventually grows into a physical water droplet. These are so small and so sparsely populated, they are often imperceptible to the naked eye. Also, droplets with sulfur typically reflect more sunlight than droplets without. For this reason, sulfur might present a beautiful solution to the climate tipping problem. This would be aided by three tricks, which we will now review. Sunlight is mostly reflected by the water in the droplet and not the sulfur. In other words, water amplifies the impact of the sulfur and therefore reduces cost. The temperature of the atmosphere varies in unobvious ways. A plot of temperature versus altitude shows that it gets colder as we go up. However, This reverses at a 20-kilometer altitude since ozone at that height absorbs heat and causes temperatures to become warmer as one goes even higher. This means we get a layer of relatively cold air at a 20-kilometer altitude. Also, warm air rises, which means that a material injected at this altitude will go up and not quickly fall to Earth due to gravity. In other words, sulfur injected at a high altitude will stay there for a year or two and dramatically reduce planet cooling costs. As noted previously, sulfur is harmful to both people and oceans. Therefore, the public is not inclined to increase sulfur emissions. However, that is not being considered. Instead, we are looking at harvesting sulfur from fuel products before combustion, transporting the harvested sulfur to an airport, transferring it to an airplane, and emitting it at a very high altitude. In other words, total sulfur emissions do not increase, and instead, emission location changes, global cooling increases, average ocean acidity stays constant, and health improves due to less sulfur near people. Here's an example. In scenario 1, a refinery makes fuel for ships and outputs 200 tons of sulfur each day, which is eventually emitted at sea level. And in scenario 2, the refinery filters out half of the sulfur to be emitted at a high altitude. The total amount of sulfur emitted into the atmosphere is the same in both scenarios. The disadvantage of changing the injection site is cost, and this can be calculated in units of dollars per American per year. And, as noted previously, the cost of cooling the planet can be compared with the cost of not cooling the planet. For details, see this book by Wake Smith or this interview of Professor David Keith. In conclusion, we can do climate the easy way or the hard way. Our society is currently doing it the hard way. However, for relatively little money, we can do it the easy way by basic principles taught to college students. And for more climate solution videos, visit the link shown here. Thank you for listening.